We can smile at store.
Usually how it goes.
Yeah, another month, I'll just get on board.
Good. We've been uneventful, but it's good. Were you?
Good. I didn't get over it.
Okay.
Well, the comment I got was Friday night, right before we went to get dinner, we did double shots of tequila.
It's sounds like a good time. You're back in one piece too, so that's always a good thing.
Yeah, I didn't pick my guts out and the other stuff.
Good.
That was a lot of fun. Saturday we didn't do much. Sat around. Two other guys that come up, and then two of the guys that were out there with us already. They slept most of the day.
Recovering from Friday.
Oh, yeah. So my cousin and I, we just watched TV.
It's good.
And then went to one of the.
Oh, I didn't know they had breweries up there.
Two. One that is in the village.
Mm-hmm.
It's Big Bear Lake, and then there's one on the others. Pretty cool. Then they, you know,
Oh, it's raining. Oh, wow.
yeah. That was fun.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, and so it's the beginning of week 4, and so you know we're very quickly approaching what I kind of consider to be the mid-semester, which is I think kind of the busiest part of the semester. So yeah, things will probably get busy fairly soon. Probably especially for you guys, because I know a lot of you guys are seniors, so this year is just going to be busy in general. All right, so the plan for today is we're just going to continue on with our lecture notes. And so last Thursday, we introduced the idea of constraint optimization and kind of what that means and how that affects our process. And so today we're actually going to go through some problems, go through some different methods on how to actually solve these problems. All right, so some announcements. So I'm a little bit behind grading your guys' homework, so I'm hoping to grade that by tomorrow. I also haven't posted the next homework yet, even though I know last Thursday I said I would. I've had to kind of deal with a few things on the advising side this week, so haven't had a chance to do that. But I'm just about done. It's just kind of just one more problem I need to get the solutions for, and then the next homework will be done. So that should be done by tomorrow. Okay. Okay, all right. So I think that's it for my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go and get started. And so let's continue on with constraint optimization. And so just to kind of jog your memory, when we talk about constraints and optimization, we're talking about optimizations that have constraints. I have no idea where I was going with that statement. But anyway, and so a lot of optimization problems that you'll find, in practice will have constraints on the values of the design variables, right? And we can express these constraints mathematically either using an equality relationship or an inequality. So we'll deal with inequality constraints another day, probably on Thursday. But today I wanted to focus on just equality constraints. Okay. So equality constraints are mathematical relationships that have an equal sign, right? Hence the name equality constraint. Okay. And before we kind of continue, I want to kind of remind you that we can put these constraints or put these equations in standard form. Okay. So standard form for equality constraints takes the following form. Right. And so on the one hand, on the left-hand side of the equation, we have some function of the design variables. So that's where most of the equations, or that's where most of the action is going to be. Okay. And then in between these, we have an equal sign, and so that's really important. And so if you don't have an equal sign, then you don't have an equality constraint, you have an inequality constraint. Most importantly, on the right-hand side, we have zero, literally just zero. All right, so a couple examples that we went over last time, maybe we have something like x1 plus x2 0, okay? So this is a very simple example where we have two design variables, x1 and x2. And so on the left-hand side, we have an equation relationship between the two. We have x1 plus x2. We have the equal sign, and on the right-hand side, we have 0, okay? So this would be an equality constraint in standard form. So this is the form that we usually might be put our constraints. Okay. Another example that may not be in standard form may be something like the following. So maybe we have 3x1 squared is equal to 2x2. Okay. All right, so we have this is a constraint because we have an equal sign here, but it's not in standard form. Okay. And so to put this in standard form, we have to make sure the right-hand side is equal to 0. So we're going to move this 2x2 and move it over to this side of the equation. So this now becomes 3x1 squared minus 2x2 equal to 0. Okay. So now we have, this constraint in standard form. So, we're starting with equality constraints because equality constraints generally are a good thing, and so you actually like to see them in your problems because they actually make your life a little bit easier because they end up reducing the dimensionality of the problem and thus making your optimization procedure much easier. Okay. think the last example that we did last Thursday kind of illustrated this point, where I think we did an example where we started with a 3D or three-dimensional optimization with 3 design variables, and we slowly introduced constraints, and we saw that the dimensionality of the problem went down by. Okay, so that method that we actually did in our last example last Thursday is a great example of a solution procedure, actually, and so we call that solution procedure direct substitution. So direct substitution, I think, is a very intuitive way to solve, for these problems, because you literally take the quality constraint and directly substitute it into the problem. All right, question in the chat. So for quality constraints concerning just one variable, would the standard form be like x minus 2, for example, or would it just be written as x equals 2? Yeah, it's a good question. And so for those, if it's just involving one variable, the standard form would still be the equal 0. And so you would have x minus 2 equal 0. Yeah. But in that case, if you have just one variable, then you can basically just remove that from the entire optimization. And so you can you just use direct substitution, just plug in x is equal to 2. Yeah, but technically the standard form would still have the 0 on the right hand side. All right, so let me actually pause here. Any other questions on this? Okay. All right. So what is direct substitution? So direct substitution is, I will say that you can only use direct substitution for relatively simple cases. And so for relatively simple constraints where you can solve for an explicit expression for one of the design variables, you can just plug that in directly into your objective. Which is exactly kind of what we did last Thursday. All right, so I have a couple examples for this. So direct substitution, this will be kind of your best friend during this unit, just because it's probably the simplest way to deal with these cases. All right. So let's do an example. So let's say that we want to optimize the following function. Okay, so this will be a 2D optimization. So we have f of x1, x2 is equal to x1 squared minus x2 squared. Okay. So fairly simple objective function in this case. Okay. But we're going to add a constraint into this equation. And we'll say our constraint is 4x1 minus x2 equal to 7. So we have one equality constraint. Okay. And so just kind of doing just kind of the high level math here, right? We have a 2D optimization with one equality constraint. Okay? That equality constraint is going to take down our dimensionality by 1, And so this, in theory, should just be a one-dimensional optimization. Right. And so before we begin, let's go ahead and put this constraint in standard form. It's not going to matter too much for this problem, but it's a good practice to get into. Okay. And so we're very close, right? And so, on the one hand, we have 4x1 minus x2 on the left-hand side. The only thing we have to fix is that we have to move that 7 over. Okay? So the standard form for this constraint will be 4x1 minus x2 minus 7 is equal to 0. So standard forms are going to be important once we get to Lagrange multipliers, which is, kind of the subject for the second half of class. Okay. All right. But this is a direct substitution problem. So let's see if we can take this constraint and use it to substitute in for either x1 or x2 in our objective function. Okay. So that's our goal, right? And so just like you would solve an algebraic system, when you're using direct substitution, your goal is to substitute and eliminate. Okay. All right. Let me take our constraint here. So let me actually start with the standard form. This one's actually quite convenient. And we want to solve this expression for either x1 or x2, right? Because what we're going to do is we're going to take this and plug it into our original objective function. All right, so the simplest thing in this case would be to solve for x2, because we have a minus x2 here, and we can just kind of move that over to one side of the equal sign. And so if we move that x2 over, we have 4x1 minus 7 is equal to x2. And then what we have from here is we have an explicit expression for x2, right? And so based on our constraint, we say that x2 has to be equal to 4x1 minus 7. Okay? So we can go ahead and plug this back into our original objective function. So let's go ahead and do that. And so our objective function is equal to x1 squared minus x2 squared. Let's go ahead and plug in for x2. And so we plug in for x2, we have x1 squared minus quantity, 4x1 minus 7 quantity squared. Right, and so if we look at the result here, the only design variable that we have left in this expression is x1, right? So because through direct substitution, we've gone ahead and plugged in for x2 and thus eliminated it from our expression, okay? So this is really nice because now that we have this expression here, we can solve this as if it were a 1D problem. And if you recall from last week, 1D methods are a lot easier to deal with than 2D or 3D. Okay. So this is really nice, and so this ends up saving us a lot of work. This equality constraint. All right, so I'm not gonna finish solving it from here just because it's a 1D problem, but the way that you would solve this is you would take the derivative of this expression with respect to x1, set it equal to 0, solve for the value of x1 that satisfied that expression. Okay. And then you have to compute the second derivative to see if this is a max or a min. Then once you find the optimal value of x1, then you can plug it back into our constraint. So once the optimal value of x1 is found, you then plug it back into this expression here to solve for the optimal value for x2. Okay? Because what the equality constraint is telling us is that the optimal values for x1 and x2 are closely related according to that equation.
What's the 10 methods?
Wait a second.
What are the 10 methods?
The 10 methods?
Yeah.
Oh, that's a 1D.
Okay.
Yeah.
Yeah.
I was like 10 methods, like, oh, I haven't I don't even know 10 methods. Yeah, this is 1D. Maybe I'll write it like this. 1. There you go. So that's the general playbook for direct substitution. So we're not going through kind of the actual method of solving this, just because I wanted just to highlight from this how you would do direct substitution. Okay. The next example we are going to actually work with, because honestly the next example is more interesting. This is just kind of an equation I just made up, but the next problem is cool. Okay. Any questions on this example here? Okay, all right, so let's do the next example. All right, so this next example may be something that you've wondered if you're a weird kid like me, but we can actually solve this using constraint optimization. Okay. All right, so for this example, let's imagine that you have a sphere. Okay. Maybe it's like a soccer ball or a basketball or something like that. Okay. And you want to find out, what's the largest box that you can fit inside that sphere, and what are the dimensions of that box? Okay. So just for simplicity, we'll assume that our sphere has a radius of 1. Okay. It's 1 meter, 1 foot. We're not using units here. All right, and so the kind of the figure that goes along with this is that we have a sphere. And then inside the sphere, we want to put a box. So there's our box inside the sphere. All right, so the dimensions for this box, we're going to make it a little bit weird, just to make it convenient for our calculations. And so let's say that this entire system is centered on the origin. Okay, so our origin is at the center of the sphere. And we're going to assume that the box is centered on that same origin. Okay. Okay, so this is the x direction, this is the y direction, this is the z direction. Right. And so our design variables in this case, based on the problem statement, our design variables are going to be the dimensions of the box, right? So the height, the width, and the depth of the box. Okay. All right. But the way we're going to define these dimensions is, based on its distance from the origin. So, we're going to assume that each length of the box has a length of 2 times the design variable, right? So this is going to be 2, the height is going to be 2x1. The width is going to be 2x2, and the depth is going to be 2x. Okay. And the reason we have the 2's there is because of this coordinate system that we chose, where the origin's in the middle. Okay. So each dimension of the box is 2 times xi, where I is either 1, 2, or 3. Okay. And so because this is a 3-dimensional problem, we have 3 design variables here. That means our optimization is also going to have three dimensions. Okay. So that's already kind of troubling because we've never done a 3D optimization before, right? We know the methods for it, and so all the multidimensional methods that we learned previously can apply here. It's just going to be a major pain in the ass to do it for 3 variables. Okay, so we want to try to reduce this as much as possible, and so let's try to use kind of the logic of the problem to see if we can form an equality constraint. Right, so that's our objective. So we have an optimization problem here, but we're going to first, before we actually try to solve the optimization, we're going to see if we can simplify it. Okay. But first, though, before we get into that, let's go ahead and write out our objective function. Because it wasn't given to us explicitly in the problem, although we can kind of imply it based on the wording of the problem. Okay. Okay. And so if I scroll back up here for a second. And so the problem is asking us to find the dimensions of the largest box. Okay. And so the operative word here being largest. And so our objective function should kind of reflect this goal, right? To find the largest box. Well, one way that we can measure largeness or size is the volume of the box. Okay, so let's use that for our objective function. And of course, based on the problem, we want to maximize this volume. maximize objective function has three variables for now. Okay, so f of x1, x2, x3. Okay. And it's going to be the volume of the box. And so the volume is actually quite simple. So we're just going to take all three dimensions and just multiply them by each other. Okay, so you have 2x1, 2x2, 2x3. Okay. And so if we kind of multiply this out, we have 2 times 2 times 2, which is 8. x1, x2, x3. Okay. So this right here is our objective function. And we want to maximize that for this problem. Okay. Any questions on this so far? Okay. All right, so this 3D optimization, we can do it. In fact, actually, this one's actually not too terrible, just because it's, you know, we're kind of linear in all three variables. But let's see if we can actually reduce this problem. Okay. All right, so let's talk about constraints. The only constraint that we're given in the problem is that the box has to fit inside the sphere. Okay, and so this can't just be a ginormous box; it has to fit inside our sphere. And so the size of our box thus that's going to put some constraints on the values for x1, x2, x3. Okay. All right. And so what does this mean? And this is kind of where our weird kind of you know, the way we kind of define the dimensions of the box, this is where it's going to come. Okay. So notice how the origin is at the center of the box and at the sphere, right? And so the best case scenario is if, you know, the corners of the box are going to sit on the sphere. Okay? Because what we're saying is that if the corners of the box are aligned with the sphere, then the rest of the box is going to be inside the sphere as well. All right. And so let's think about if we can express this this scenario here using a mathematical expression. Okay. And so if we were to look at the coordinates of one of the corners, so there's going to be 8 corners of the box, right? Yeah, 4 on top, 4 on the bottom. Okay. And so all the corners of the box are going to have these coordinates. It's going to either plus or minus x1, depending on which corner that we're at, plus or minus x2, plus or minus x. Okay. Okay. So let me go ahead and illustrate that for you here. Origin, center. If we look at this corner right here, the one that's kind of right out in front, the coordinates for this is going to be x1, x2, x3. Okay. Remember the lengths of each side here are x2x1, 2x2, 2x3. The coordinates of this one right here, this would be, kind of mix it up a little bit. And this would be minus x1, x2, x3, okay? And so depending on what corner that you're in, you might have a negative in front of the coordinate, okay? All right. And so if these corners are going to be sitting on the surface of the sphere, that means the distance between the corner and the origin has to be 1. Remember, our sphere has radius 1. And another definition for a sphere is that the sphere is the collection of all points that are equidistant from the center of a sphere. Okay. And so for a sphere's radius 1, that every point on the sphere is distance 1 away from the origin. All right, so let's express this statement here mathematically. So let's use the distance formula. So we want the distance between the corner and the origin. So the distance between the corner and the origin would be x1 minus 0 squared plus x2 minus 0 squared plus x3 minus 0 squared. And this is equal to 1. And so of course the minus 0 that is going to go away, so we have x1 squared plus x2 squared plus x3 squared equal to, so this right here is the constraint for our problem. Okay. So this is kind of the mathematical kind of expression of the fact that the box has to fit inside the sphere. Any questions on how we obtained that formula there?
Can you just may you please explain again the equation that's right above the circled one, right above our constraint?
Sorry, Jeremy, could you repeat that? The volume is a little bit low on the podium.
Yeah. Are you able to explain the equation above our constraint equation?
This one right here, the this distance formula equation.
Yeah.
Yeah, so that's just the distance formula in 3D. Well, I guess we're missing the square root here. And so the distance formula is always going to be, if you have 2 points in 3D space, let's say this is XA, XB, XC, and then this is another point in 3D space. We'll call this XD, XE, XF. And we want to know the distance in between these points. Then our distance formula is just the difference between the corresponding coordinates. And so both the x coordinates here are going to be XA minus XD, and then we square it. And take the difference between the y coordinates, which is XB minus XE, 1 squared, plus difference between the z coordinates, which is XC plus F squared. And this is equal to the distance in between. So the distance in between, we'll call R squared. Okay, so I just apply that distance formula, except the second point, instead of XD, XE, XF, I have the origin. So the origin has coordinates 0, 0, 0.
Got it. Thank you.
Yep. Any other questions on this expression here? Okay. All right, so we have our constraint. So let's use this to use direct substitution back into our objective function. All right, so we're going to solve this constraint. So we're going to solve for one of the design variables. In this case, it doesn't really matter. All three of them are the same. So we have x1 squared, x2 squared, x3 squared. So I'm just going to pick one. So I'm just going to pick x3. Okay. But you could have easily done x1 or x2. The choice of x3 was arbitrary. So we're gonna solve this for x3, then plug this back into our objective. Okay. And so to solve this expression for x3, I'm gonna subtract x1 squared and x2 squared from both sides. So you have x3 squared equal to 1 minus x1 squared minus x2 squared. And of course, we have to take the square root. So let's go ahead and plug this back in. Remember, our objective function in this case is 8x1, x2, x3. We plug in for x3, we get 8x1, x2, square root 1 minus x1 squared minus x2 squared. So now what we have here, what I have circled is our same objective function. It's just that now instead we've used our constraint to reduce its dimensionality, right? And so instead of a 3D problem, we have a 2D problem. And we can solve this using our 2D methods. Right, so you might think that, this still seems like a very difficult problem, right? Because we have a square root and squares, but the difference between a 2D and a 3D problem is huge, especially when we go to compute the Hessian. This is going to actually save us a lot of time. And similarly, the difference between a 3D problem and a 4D problem is ginormous, right? And so, whenever you're doing optimization, it doesn't matter if you're doing the classical methods like we're doing now, or if you're doing MATLAB methods that we're going to do, later in the class. If you have the opportunity to reduce your dimensionality by 1, you take that chance every single time, just because the amount of effort and the amount of time that you save is always going to be, it's always going to be worth it. Okay, and that's even more true for all the later. Okay, so we have a 2D problem here, and so to solve this, we're going to take our partial derivatives with. Take partial f, partial x1. We're going to set it equal to 0. And we're going to take partial f, partial x2, and then also set it equal to 0. Okay. All right. And so the unfortunate thing here is that because our objective function is in the following form, we have to use product rule and chain rule to take its derivatives. Okay. All right, so I'm actually going to separate this into 2 expressions just to make it kind of clear. Okay. So we'll call this part A, this part B. Okay. So first thing we're going to do is take the product rule. So remember, product rule is going to take B partial x1 part A multiplied by B plus partial x1 of B multiplied by A by itself. Okay. All right. And so if we take the derivative of part A with respect to x1, we're just taking the derivative of 8x1 x2. Okay. So the x1 is just going to cancel out, and so we have 8x2. And then we're going to multiply it just by B by itself. Okay, so this will be multiplied by 1 minus x1 squared minus x2 squared plus we have the derivative of part B. And so part B, we have the square root of 1 minus x1 squared minus x2 squared. Okay, so we're going to have to use chain rule here because the x1 is kind of buried inside the radical. All right, so using chain rule, let me go ahead and figure this out just to give myself more space. Okay, so using the chain rule here, we're gonna have a 1/2 that comes out from the outer derivative. Okay. Then we have derivative of the outer expression. So the outer expression is 1 minus x1 squared minus x2 squared. Okay. We take the derivative of that, our exponent of 1/2 becomes minus 1/2. Okay. So that's the derivative of our outer expression. So now we take the derivative of the inner expression. So our inner expression here is 1 minus x1 squared minus x2 squared. We take the derivative of that with respect to x1, then we get minus 2x1. Okay. Derivative of outer. Inner. Okay. So that's partial b, partial x1. And then we're going to multiply it by the entirety of part A. So part A is 8x1 x2. This is part A. And so remember, this part comes out because of the product. So lots of derivative rules, and hopefully this is kind of jogging some memory. So I partially chose this example just because it has a lot of these, these derivative rules that you may or may not have forgotten. And so I think this serves as kind of a good way to review. Okay, so here we had to use both product rule and chain. All right. So let me go ahead and simplify this just because it's kind of a mess right now. Okay. And so if we simplify this, we get 8x2 side, and then on the inside we have is, from our first term here we have square root minus x1 squared minus x2 squared plus, or minus, excuse me. Because we have the minus that comes out from the minus 2x1. Okay. These 2's in the top expression are going to cancel out. Okay. And so we're left with x1 squared multiplied by quantity 1 minus x1 squared minus x2 squared raised to the minus 1/2. All this is equal to 0. Any questions on how we obtained that expression there? Because we did a lot of derivative rules.
What into the 8x1?
This 8x1, so this x1 combined with this x1 right here became x1 squared. Oops. And then the 8x2 came out in front. Yeah, good question. I kind of skipped over that part.
We are going through Bayesian rule, right?
Wait a second.
We are going through Bayesian matrix here.
No, so actually we're not even there yet. So we're just taking the first partial derivative to find out where the extreme are.
Oh,
Yeah, so we're taking the first derivative, setting them equal to 0, and then solving for x1 and x2 at those extremes. Yeah. It's just there's a lot of derivatives that occur, so it takes a while. No, we're gonna skip the second derivative, so that'll take even longer to do. All right, everyone kind of follow how we got to arrive here. Okay, all right, so let's do the same thing for the other partial derivative. So we have partial f partial x2. And we set that equal to 0. Okay. And so same thing, we're going to take partial x2 of section A multiplied by b plus partial x2 b multiplied by a. Okay. So we're going to do the same product rule we did for the first partial derivative, except now we're taking derivatives with respect to x2. Okay. All right. And so, because of the symmetry in this problem, the details of the math are going to be almost identical to the one above. And so just for the sake of time, just because I want to get to Lagrange multipliers today, I'm going to go ahead and skip that. And so this is going to be very similar to above. Okay. And then from this, we're going to get an expression that looks very similar to above, except x1 and x2 are going to be swapped. Okay. All right, and so we work through all that algebra and all that derivative taking. We end up with 8x1 multiplied by quantity 1 minus x1 squared minus x2 squared minus x2 squared times square root, or excuse me, 1 over square root of 1 minus x1 squared minus x2 squared to the minus 1/2. And it's all equal to 0. So these two equations here, so we have this one up here, and this one down here. Okay. We need to solve these two expressions for x1 and x2. So let's go ahead and do that. All right, so we have two equations and we have two unknowns here. So in theory, we should be able to get the answer. Right? In theory is the operative word here, because the algebra here is going to be ugly. But I'm going to do a little trick here just to make things a little bit easier for us. Okay. If you notice, one of the main difficulties with these expressions is because of the square root, right? So we have square root of 1 minus x1 squared minus x2 squared. Right. In fact, we have a square root on one term and a 1 over the square root on the other. So let's, since both of these equations are equal to 0, we're kind of free to multiply both equations by whatever we want to simplify. And so our first order of business should be to get rid of the square roots, because the square roots are making it very difficult to solve this. And so we can actually get rid of both square roots by just multiplying by the same square root. Okay. We're going to multiply both equations by square root of 1 minus x1 squared minus x2 squared. Okay. And so this is to simplify the square root. So I'll show you the math for the first one, and then you'll see that kind of the same thing applies for the second one as well. Okay. So our first equation is partial f partial x1, and this is equal to 0. And so this is equal to 8x2 multiplied by square root 1 minus x1 squared minus x2 squared minus x1 squared times 1 minus x1 squared minus x2 squared negative 1/2 power. And so we're going to take this expression, this entire equation here, and we're going to multiply it by 1 square root of 1 minus x1 squared minus x2. And so let's see kind of what that does to our entire expression. And so let's start on the let's start with the 0 side. And so we have 0 multiplied by that. That's very simple. And so we just end up with 0 on that side of the equals. Okay. We have the 8x2, so that's kind of staying the same because we're going to distribute the square root into the middle of the equation. Okay. All right, so let's look at this term first. We have square root of 1 minus x1 squared minus x2 squared multiplied by square root of 1 minus x1 squared minus x2 squared. Okay, so we have the square root of the same thing multiplied by each other. Okay, and so when you have the square root of the same thing multiplied by each other, the squares are going to cancel out and you end up with just whatever was on the inside. Okay, so it's going to become 1 minus x1 squared minus x2 squared with an exponent of 1, which is beautiful because we love exponent. All right. So then we have the second term there. So the second term is x1 squared multiplied by quantity 1 minus x1 squared minus x2 squared raised to the minus 1/2. Okay. And remember, we have when you raise something to a negative exponent, it's like the same thing as taking its reciprocal, right? And so it's like we have square root of 1 minus x1 squared minus x2 squared in the denominator. Okay. And so if we have that expression in the denominator and we multiply by the same thing in the numerator, those two things are going to cancel out. Right? So this is going to cancel out this. And so that actually simplifies our life a lot. And so we just end up with x1 squared. All right, and so if we simplify this a little bit more, we're just going to take just minus x1 squared minus x1 squared. We get 8x2 divided by quantity 1 minus x2 squared minus 2x1 squared. We're going to do the exact same thing to the other equation. So for the other equation, we're going to multiply by square root of 1 minus x1 squared minus x2 squared. Okay. And then what we get from that is 0 is equal to 8x1 multiplied by 1 minus x1 squared times 2x2 squared. Okay. All right. So I'm going through all as much of the algebra for this one as I can, just because for your next homework, you're going to be doing a lot of this work. And kind of what I've seen, of course, this is my first time teaching this class, but kind of what I've seen in other classes that kind of people kind of get caught up in the algebra and solving for equations. So, I want to make sure I kind of go through this example kind of in detail, just so you can see at least most of these steps, just so that you have the confidence to kind of, carry this through on homework. Okay. I will say that this problem is more difficult than the homework problem. So if you can do this one and you kind of understand everything, then homework will be easier. All right, any questions on how we obtain this result here? Okay. All right, so now we have these two, so now these are our two equations. Okay. And they're a lot easier to solve than before. Okay. So let's do this. So let me start out with this bottom one here. Okay. And we are again going to take advantage of the fact that we have 0 on the left hand side. And so, this next step here, we're going to make the assumption that x1 is not equal to 0, which is a reasonable assumption. Okay? Remember, x1 here represents the dimensions of a box, right? And so it doesn't make sense for our box to have a length of 0 or width of 0, right? Because then we wouldn't have a box, we'd have a square. Okay? So since x1 is greater than 0, let's divide both sides 8x. Okay. We're just going to eliminate 8x1 from this equation. If 0 is equal to 1 minus x1 squared minus 2x2 squared. Okay. Let's go ahead and move x1 over to one side of the equation, and so we get x1 squared is equal to 1 minus 2x2 squared. All right, so now that we have this expression for x1 squared, I'm not going to bother taking the square root just because I know in my other equation here I have x1 squared, and so we can just plug in straight for that. And so let's go ahead and plug this into our other expression, and then we'll be able to solve for x2. Okay. All right, so same thing with the other equation. So I'm going to use pink for this. Okay. So our other equation is 8x2 times 1 minus x2 squared minus 2x1 squared. Okay. All right, so same thing as before, I'm just going to divide both sides by 8x2, so that eliminates that. And then for x1 squared, I'm going to plug in what we just found here. Okay. We have 0 is equal to 1 minus x2 squared minus 2 times 1 minus 2x2 squared. All right, so let's go ahead and distribute that minus 2. So we have 1 minus x2 squared minus 2 plus 4x2 squared. So finally, we arrive at something that we can solve kind of very simply, right? And so the 1 and the minus 2, those two combined is going to be minus 1. We have a minus x2 squared and a positive 4x2 squared, so that's going to be a plus 3x2 squared. Okay. This is equal to 0 still. So I'm going to add 1 to both sides of the equation. I'm going to divide by 3, take the square root. Okay, so I'm just going to combine all 3 of those steps together. So I think there's that. And we finally get x2 is equal to square root 1 over 3. All right. Long process to get here. All right, now that we have a solution for x2, we can go ahead and plug that back in and solve for x1. All right, so we have x1 squared is equal to 1 minus 2x2 squared. Okay. We plug in for x2 squared, and we get 1 minus 2 over 3. And so we get x1 If the square root of both sides is equal to square root of 1 over 3. Okay. And then finally, remember, we started this problem as a 3D problem, so we have to solve for x3 as well. So let's plug these back into our constraint to solve for x3. Okay. We get x3 is equal to square root 1 minus x1 squared minus x2 squared. Okay. This is back from our constraint. So we plug this in, we get 1 minus 1/3, 1/3. We get x3 is equal to also square root of 1. So the biggest box that we can put inside the sphere has lengths of 2 times square root of 1 over 3 on all sides. Okay, so it's a square, it's a cube basically. And that kind of makes sense. All right, any questions on how we finish up this problem here? Yeah.
So could we have used another constraint that the cube's gonna have equal sides
Mhm.
and made this even simpler?
So the main thing for this problem is that it has to fit inside the sphere. And so if we use another constraint where all 3 had to be the same, you know, we wouldn't kind of incorporate that sphere. Unless you're asking if we use the same constraint as before with the sphere, but we added the additional constraint of that all 3 of them have to be used.
Yeah.
Yeah, actually that in this case, we would get the same result. But that information about all 3 being equal, you know, maybe it wasn't obvious kind of when we started the problem. And so, you know, it would be hard to kind of justify that before. Now that we're done with the problem, like, yes, you know, we could put that constraint and make our life easier, but you know, you kind of have to be careful about kind of what the problem gives you and what you can actually apply. Right. Okay, so one last thing for this example, we're not quite 100% done yet. We have to make sure that this is a maximum, right? So we found the extrema, right? So we found the extreme point where, you know, we have a value for all 3 design variables, but we have to check if this is a maximum, right? So it would feel kind of silly if you go through all this work, and this is actually the smallest box that can fit inside the sphere, right? So we need to use the Hessian. We need to compute the Hessian to ensure that this is a maximum. Okay. Don't worry, it is a maximum. You know, we didn't go through all this effort for nothing. Okay. So I'm not going to go through all the details of that just because that's, you know, it's going to involve more power rule, more chain rule, and you know, more pain than, you know, we have time for today. So we're out of time for pain, and so we only have time for happiness. So I'm going to give you the Hessian here. Okay. And so if you do go through that, I went through it when I prepared these notes, but I didn't include the details. And so the Hessian is negative 32 divided by square root of 3 minus 16 over square root of 3, 16 over square root of 3. That's 32 over square root of 3. And because of our constraint, we can use a 2x2 Hessian. Okay. We don't have to do a 3x3, which would be even more awful. Okay. And remember, you know, to make sure this is a maximum, our Hessian has to be negative definite. Okay. And the good news for this, for this case is that this matrix is negative definite. So if you take the determinants of all the principal submatrices, you'll see that the first one is negative, right? We see that right away when our top left entry here is negative. And then when we go to the next, the next principal submatrix, you'll see that it's positive. Okay. And so when we have alternating, determinants, that means our matrix is negative definite, and thus we have a max. Okay. Now we're done with this problem. So now we're completely done. We can go ahead and move on to the next. Okay. Okay. But that's direct substitution in a nutshell. Okay. And so through all of the derivative kind of mathematical details, I want to make sure that you guys know that when you have problems with equality constraints, or you can just kind of directly plug it in, that's called direct substitution. And that's usually a good way to go. Because it's kind of the simplest way to deal with equality constraints. Okay. The downside of direct substitution is that it's not always going to work. Okay. And so if you have equality constraints where the expression is very complicated or it's hard to plug in, then you're going to need to rely on another method, which is called Lagrange multipliers. Okay. All right, so Lagrange multipliers is a parallel technique. It's not it's not in addition to direct substitution. It's just an alternate path. Okay. So it's an alternative approach. Okay. And so unless the problem kind of directly specifies that you have to use Lagrange multipliers, if it's easier to use direct substitution, then I would just go ahead and use that. Okay. And in fact, in the homework, I give you the option. And so I'm giving you two constrained optimization problems with with equality constraints. So you can either use direct substitution or you can use Lagrange multipliers. Okay. In a lot of instances, the Lagrange multipliers are going to be slightly more work than direct substitution. But I'm bringing them up because they're kind of a prerequisite for our final topic, which is the Kuhn-Tucker conditions. Okay. And that's when we do inequality constraints. And so the Lagrange multipliers by themselves, you may look at them and think, this is kind of a lot of work. But we need to kind of learn them to learn the next time. Okay. Okay. So the idea with Lagrange multipliers is that, we're going to take all of our equality constraints and we're going to incorporate them directly into our objective function. So up to this point, our equality constraints has kind of been something separate, right? And so we have our objective function and we have our equality constraints, and we kind of deal with them kind of separately. Okay. So the idea with Lagrange multipliers is, why don't we take our equality constraints incorporate them directly into our objective function with a small caveat. Okay. And that caveat being that we have to multiply our objective constraint by, or excuse me, we have to multiply our equality constraint by a new factor called the Lagrange multiplier. Right, so it kind of looks like this. Right, and so instead of optimizing the objective function by itself, we're going to optimize a new function called the Lagrange function. Okay. And so the Lagrange function is a function of two things. And so we have our original design variables, and so this x vector here, that's our vector of design variables, and we also have our new factors called our Lagrange multipliers. So these lambdas here, these are Lagrange. So it's like this. And so our Lagrange function, we're going to have our original objective function, which is just a function of our design variables. And then to that, we're going to add all of our constraints. And so we have a summation is equal to 1 to m, and I of x. Well, remember these GIs. These GIs here, these are our equality constraints in standard form. And notice that we're multiplying each one by a Lagrange multiplier lambda I. Okay. Okay. And so just one last quick point. So the only reason this works is that, remember, in standard form, we made our equality constraints equal to 0, right? And so if we look at this expression here, it looks like we're adding a lot of complexity, but technically each of those g functions are equal to 0 because our equality constraints are in standard form, okay? And so the argument here is that by optimizing this Lagrange function and finding the optimal of this is actually the same thing as finding the optimal of our original objective function, because each of the equality constraints is just equal to 0. Okay. All right, and so when we come back on Thursday, we'll look at the details of how this is done. We'll do a couple examples of this, and then we'll compare it with the direct substitution method. Okay. All right, so thank you guys for coming today. I know that today there was a lot of derivatives and algebra, but hopefully seeing that example in detail was helpful for you guys, right? And so on Thursday we'll pick this up. And so I hope you guys enjoy the rest of your day, and I will see you all on Thursday. Wando, any final questions? I was just here. Assuming you have any questions. All right, I'll see you guys on Thursday.